Good. Thank you. Is it okay with the audio? Good, okay. Thank you for the very nice introduction. It is my first time in Taiwan, and I like it a lot. And I'm very glad that Jen's group hosted me during the first half of the visit, and I'm happy now to visit Ken Chen's group for the second half of my visit. And and I'm also very grateful that I can present some of our very nice institute. So this talk should be more like a conversation opener. So we can always continue discussing things later on, also via email. So there's so many things to mention, and only a finite amount of time. So that's why if there's something interesting to discuss, we can also continue discussing things later. In the past years, I've been I've published 2 papers on very exotic type of explosions that we think are connected with the explosion of extremely massive stars. And these kinds of explosions, they're not the regular supernovae. They're called Pair-Instability Supernovae. And Ken Chen has led a lot of work in this field. And one of the puzzling things, or one of the outstanding questions has been, how do they look like? How common are they? What are their properties? And in the past years, we found a few objects that match many of the predictions, but there are still a lot of open questions remaining. And so it's an interesting, we're at an interesting point for observers and theoreticians where we need to discuss, okay, which kind of observations are needed to advance that field, and also maybe which kind of questions would be interesting to answer from the theoretical sides that are important for observers to make further progress. So this cartoon nicely summarizes what this talk is about. So on the top row, you can see a very simplistic picture of how massive stars evolve. So they start as a ball of hydrogen. In their course, they fuse hydrogen to helium, then helium gets fused to carbon, and so on and so on. So by the end of the life, an ion core has formed, and the star is not able to prevent this ion core from collapsing, so a supernova explosion happens. And this works for many of the core collapse supernovae that we observe, or for most of the core collapse supernovae that we observe. However, very massive stars have a slightly different evolution. And so they're also born as balls of hydrogen. They also fuse hydrogen to helium and helium to carbon and so on in their course. The interesting thing that's happening is during the oxygen burning phase. So during that phase, the temperatures and the densities are in such a nice regime that photons are converted into electron-positron pairs. And this reduction in photons means the radiative pressure is decreasing, and this radiative pressure is balancing the star against the gravitational pull. And with this instability, the star shrinks and explosive nucleosynthesis can happen. If a star has a mass between 130 to 260 solar masses, this instability is so violent that it disrupts the entire star, leaving no remnant behind, but it produces a brilliant supernova explosion. If the star was between 70 and 130 solar masses heavy at the time of birth, then this pair-instability episode is not terminal in that sense. So the star will lose a lot of mass, but it will not explode. And this can happen a few times, and eventually the star will collapse to a black hole. So I would like to say a few more things about positional pair-instability and also pair-instability supernovae, that you're getting a bit more familiar with what are some of the key features of that and why these things are interesting. And if you say, okay, well, supernovae are not my cup of tea, these kinds of objects are actually quite important for several fields in astrophysics, going from even including gravitational wave physics. So first, the pulsational Pair-Instability supernovae. So in this plot, you can see, well, you have two axes. This is the important one. You see the central temperature as a function to time to collapse. This is in logarithmic timescales. So here we are 100 seconds, or 100 times 10 to the 7 seconds away. So, and you can see there are these spikes in the temperature. This is when a Pair-Instability episode happens. So, so the star goes through this instability. The core heats up, but then it puffs up because it loses mass. Temperature drops. Then it goes through this a few times. The exact number, how often a star could go through this kind of evolution is very sensitive, or depends on the mass of the star, and also on lots of microphysical and also computational issues. And but the punchline here is, you can have stars that can go through this Pair-Instability episode more than once, and each of these episodes is connected with mass loss, sometimes more, sometimes less. These mass ejections have typically velocities of a few thousand kilometers. So this is quite fast, but it's not. But it is also the kind of velocities that you see in stellar winds and so on. So, and as you can imagine, not all of these shells have the same velocities. Sometimes they can collide. And when they collide, the collision can produce supernova light curves, like you can see here. And they very much look like supernovae based on energetics, based on the timescales. But instead of having an exploding star here, you see the collision between two shells that the star ejected at some point of its evolution. In the past years, a few candidates have been published. So I will talk about supernova 2021 YFJ in one of the next slides, because this is a very puzzling object, and but also a few others have been found, and they are not less interesting. They are also quite interesting. So when in contrast to that, if you have a full-blown Pair-Instability supernova, what happens is that the star is so massive and the instability is so strong that during this instability episode, the entire star is disrupted. The important thing is that during this instability, the star is disrupted and no remnant is formed, no stellar remnant is formed, no black hole, no neutron star. And that's different to pulsational Pair-Instability supernovae that are expected to leave a black hole behind, and also for more massive stars, they're also expected to leave a black hole behind. So there is a regime in stellar evolution where a massive star has no remnant. So Pair-Instability supernovae come in different flavors. We can distinguish them between hydrogen-rich and hydrogen-poor, so depending on what we see in the spectra. Examples for hydrogen-rich Pair-Instability supernovae are shown in this and that panel. The difference here is that the progenitor star here lost most of its hydrogen envelope. It still has some hydrogen, but it lost most of it. And then it's somehow similar to a blue supergiant. That's why these models have here start with a B. And you can see here the numbers indicate the mass at the time of birth. So it varies between 150 to 250 solar masses. Similar here. Here the progenitor retained most of its hydrogen, and so these are rather than, let's say, puffy stars, and they're then more similar to red supergiants, and again with masses between 150 to 250 solar masses. The common feature of these light curves is that they have very long rise times of a few hundred days. This is not an ordinary core collapse supernova. They only have rise times maybe of 2 weeks or so. So very, very different. In terms of luminosities, there's quite some spread. And the brightest one, they can reach luminosities of that are comparable to what we call superluminous supernovae. On the other extreme, we can stripped stars can also experience a full-blown pair-instability supernova, and these stars, these are helium stars, so they have this is like a carbon-oxygen core with a little bit of helium on the surface, since these stars are stripped, they have less mass, so they vary between 70 and 130 solar masses. Again, the rise times very long, of at least 100 days, and in terms of, and this is dictated by the very large ejecta masses, and the luminosities can vary by 2 orders or 3 orders of magnitude, depending on how much nickel they produce. And I should mention here, these explosions, they are able to produce these very luminous transients because they can produce up to several 10 solar masses of nickel. So this is starkly different to an ordinary core collapse supernova, where only a fraction of a solar mass is formed. You cannot do this with any other mechanism. So, why are pair-instability supernovae interesting? So they are a direct prediction of stellar evolution. And I should mention here, this was predicted in the 60s of the last century, or if you want to say it even more extreme, in the last millennium. So, but so far no candidate has been found. So confirming the existence, measuring the properties is actually an important step for validating a part of the of stellar evolution that we couldn't test yet. So because the full-blown pair-instability supernovae do not leave a black hole behind, but stars that are slightly less massive and slightly more massive, then the mass range for the full-blown pair-instability supernovae leave black holes behind. This means that there should be a dearth of black holes. And that's something that can be measured by LIGO. And there has been an ongoing debate, is there a dearth of stellar masses in a certain, a dearth of black holes in a certain mass range? I don't know what the if there's a final conclusion yet, but the confirmation of the existence of pair-instability supernovae and the interpretation of the LIGO black hole mass function is intimately related to each other. If you say, okay, well, I don't care about all of that, I'm interested in high-redshift universe, then these guys are also very important for you, because you need very massive stars. These very massive stars might not exist in our local universe anymore. But because in the early universe, the universe was less chemically enriched, means that the conditions for forming such massive stars were more suitable. This means we expect that pair-instability supernovae and also pulsational pair-instability supernovae were more abundant in the early universe. And then the natural question is, okay, if they're more abundant, so are maybe then the are population-free stars related to, with some of those? What is the impact of the dust production of pair-instability supernovae on the dust budget and so on? And yeah, although I haven't mentioned any of your papers yet, you have done a lot of work on all of those questions, and I'm sorry that I didn't put it there. So in the past years, candidates have been reported by the community, and usually these objects got heavily scrutinized. That's absolutely that's the proper approach, but it also meant that a lot of the candidates that, or actually all of the candidates were proposed, they were not, the community didn't conclude that these are genuine or ironclad pair-instability supernovae. And a few of those examples are shown here. And the common theme, or the reason why these objects got rejected is some have incomplete data sets, so we only have the decline. We don't know where the peak is. We don't know how the rise looked like. Other objects evolved very rapidly, much faster than what these pair-instability supernova models predicted. So when we look at the spectra, if you have, or if a supernova produces up to several 10 solar masses of nickel, then you would expect to see a lot of absorption by ion group elements. Not just in the UV, it would extend all the way into the optical. And that's why the models, one of them is shown here in blue, show essentially zero flux even at blue wavelengths, but then beyond 5,500 angstrom, we start to see strong features. So candidates that show then a significant flux excess or significant flux in the blue, they were kind of excluded based on that argument. And last but not least, a few objects only have photometric typing. They have broad light curves, and their light curve match predictions of Pair-Instability supernova models, but we don't have spectra. And so it's hard to say what is actually the true nature. These could be objects, or the nature of these objects could be related to something we haven't even detected yet, or we don't know about yet. So, so in essence, the observer community has tried to find compelling candidates for Pair-Instability supernovae. The reality is actually is not so positive. None of the candidates is deemed as an ironclad Pair-Instability supernova. But one of the objects that I will show you in the next slides matches all of the predictions, but requires some rethinking from the theory side. So, and this brings me to this wiki transient facility. In terms of green level, it can very nicely compete with Taiwan. It's also very lushly green, and so Mount Palomar has several telescopes, and Caltech has roboticized their 48-inch telescope in the past almost 2 decades, and in 2018 they equipped the 48-inch telescope with a new wide field camera. It has a field of view of 47 square degrees. In addition to this, it's also very sensitive, and this allows it to map out the entire northern night sky that is accessible at a given time with a cadence of 2 to 3 days. And this is something that didn't exist. And the important thing is also the depths are sufficiently deep so that you can probe larger cosmic volumes. In addition to this, Zwicky as a LSST Pathfinder mission did not only produce images, it also generates for every new or for any transient source in a given image a little text file, and this text file contains a little cathode. How does the field look like? How did it look when a reference image was taken? What is the difference between those two images? What is the brightness? What are the coordinates? And so, and the reason why this is so important is that instead of people doing a lot of manual work in inspecting candidates, you can now write sophisticated data mining techniques to look for transients of interest. And the nice thing is also, because these text files always exist, you can rerun the entire survey at any given time, where you just vary a little bit, not a little bit, where you vary the selection function and wonder, okay, which kind of transients are now passing your selection criteria, or why certain objects are not passing your selection criteria. So with these technological advances, CTF has transformed supernova science fundamentally. Since June 2018, it has discovered over 10,000 spectroscopically confirmed or classified supernovae, so most of the supernovae that we know today. And with this huge data set, you are able, everybody's able. So it's the important thing is it's a private-public partnership. So everybody can use these data, and with this you can map out the parameter space of known supernova classes. You can look for maybe new types of transients that you didn't know about. You can also directly target regimes of the transient phase space that was inaccessible before. And because the cadence is so high, you can, for instance, look for for supernovae or catch supernovae within 1 to 2 days after explosion. And the idea is not that you that you reprocess the entire survey and be like, okay, and conclude you have 10 supernovae detected within 1 to 2 days after explosion. No, you want to detect them and immediately trigger follow-up observations. This is our aim, and several groups have demonstrated that this is possible, and there are lots of interesting science questions related to that. And one of the examples that you will see is was detected by the Infant Supernova Program. So, but let's start with the Supernova 2018 IBB, and this is to date the best example of a pair-instability supernova. So it's as close as we ever got to actually to something that we call pair-instability supernova. The redshift is fairly moderate. It's only 0.17. It's not redshift 1, 2, and so on. So what caught our interest was the long rise by at least 90 days. It's a lower limit because the supernova happened while the field was behind the sun. So we're only we're not capturing the true rise. So, and then since peak, the light curve was declining by roughly 1.1 magnitudes per 100 days, and this is the slope, or this is a slope that radioactive cobalt-56 would produce. So the important thing is we see this slope going from the time of maximum all the way out to 600 days. Here it's a bit faster. That's okay. But this is a completely new quality. None of the other candidates has ever shown such properties. So when we overlay models for pair-instability supernovae, which are shown here in color, the takeaway message is that if you have models with between 120 to 130 solar masses in helium stars, you can capture the rise, the peak, and all the way of the decline. And this kind of match is starkly different to any of the previous candidates. These models, they were calculated a long time before this object was discovered, so it's not a fine-tuning issue. So they produce between 26 and 44 solar masses of nickel. So we are here really at the upper end of pair-instability supernova models, but it's fully consistent. However, the picture is, or nature turns out to be a bit more complicated than we thought. So we do not only have excellent photometric data, we also have excellent spectroscopic data going from roughly the time of maximum out to 600 days after peak. This means we have high resolution spectra and also high signal-to-noise spectra. So this spectrum here, which is shown in black, was obtained at roughly 287 days after peak, which is close to 400 days after explosion. And in red you can see a model spectrum for the helium-130 model that matched so nicely the light curve at roughly 400 days after explosion. So if you would ignore the blue part, you could say that the match is quite convincing. But there's a problem here. We observe a significant flux excess. And this is somehow reminiscent of the previous candidates. When we go to an even later epoch, this flux excess is even larger. So based on that, we would have concluded this is not a compelling candidate. Because if you have 25 to 44 solar masses of radioactive material, you should see line blanketing. You should not see this blue excess. So, but this is where nature shows us that it's that things are a bit more complex than we thought. So, some of our data were obtained with the X-shooter spectrograph at the VLT, and the nice thing about the spectrograph is it has a very high sensitivity in the U-band, and so we obtained a high signal-to-noise spectrum at the time of maximum, and we saw supernova features, great. We saw absorption lines from the host galaxy as expected, but then we detected a third absorption line system. And it's moving at around 2,900 kilometers. This is much slower than the supernova ejecta, which is moving at 8,500 kilometers. And these lines are also fairly broad, so a few 400 kilometers. And this is not what you would expect for interstellar medium in the host galaxy or in any foreground galaxy, which hypothetical foreground galaxy which might intersect our line of sight. This feature has been observed in one superluminous supernova before, and based with other observations that this object IPTF16H had, it was concluded that this absorption line system is connected with circumstellar material that the progenitor star lost before the explosion. So, based on that, we can conclude there is CSM around that supernova, or meaning that the progenitor star had some elevated mass loss shortly before the explosion. The question is now, okay, we know there's CSM, but does also the interaction of the supernova ejecta with the CSM produce some or contribute to the total emission? So you can see here a few more of our spectra covering from the time of maximum out to almost 1,000 days after peak. And when you carefully look at the spectrum, you see that starting from the spectrum at roughly 31 days or 30 days after peak, there's an emission line feature rising, becoming stronger, and it's also visible at very, very late times. Also here, something is happening in parallel. So these two features are produced by oxygen 2 and oxygen 3. And since these are forbidden lines, they cannot be produced in the ejecta. They require low density environments, which the CSM could provide. Now we know, okay, the interaction with the supernova ejecta produces a discrete set of emission lines. Does it also produce some continuum emission, in particular in the blue to describe the flux excess? So at late times, we see that there is a little bump in the light curve. We got lucky that we obtained the spectrum before, shortly after, and at the time of maximum of this bump. And you can see these spectra over here. So we can then use the spectrum obtained here and here to interpolate how the spectrum could have looked like without this bump. In black, you can see the observed spectrum at the time of maximum of this bump, and in red, the interpolated spectrum. One can clearly see that that this bump leads to an increase in the oxygen 2 and oxygen 3 emission lines, and it also produces some blue excess. We have some additional data which lets us which lets us speculate that all of this excess that you observe here is produced by CSM interaction, and therefore we propose that CSM interaction is not something that can be ignored in Pair-Instability supernova models. It's actually something that needs to be fully included, and we need to know what are the CSM masses, what are the luminosities that can be achieved. So, all right, next object, 23 IOP. At slightly lower redshift, it's a genuine hydrogen-rich supernova of type 2, not a type 2n supernova, which shows very narrow hydrogen emission lines. This object is characterized again by a very broad light curve. Again, the object or the supernova happened while the field was behind the sun. So we only know that the rise time is at least 100 rest frame days. So again, something that we only expect for Pair-Instability supernovae, not for other regular types of supernovae. Objects or supernova 9087A that happened in our Magellanic Clouds, it had a rise time of 100 days, but in terms of luminosity, it was 4 to 5 magnitudes fainter. In the meantime, or since the discovery of 1987A, similar objects were found, but their luminosity only goes to -17. None of them was ever so luminous. So when we do again the same game, we take our observations in G, R, and I band, and we compare it to Pair-Instability Supernova models. We get actually a good match in all three bands. However, as we include the later time data, things again turn out to be more complicated. We observed first less flux than predicted, and later we observe significantly more flux than predicted. And there's also something happening here, why it is fading so rapidly. We do not only see this in one band, we see this in all three bands. So we are again facing the situation that we are dealing here with some objects where we need a wider grid of theoretical models to perform detailed comparisons. So I would like to emphasize that this is that this supernova is spectroscopically fairly standard. So you see here one of the spectra obtained at maximum light, very high signal to noise, high spectral resolution. And when we compare it to other objects of other hydrogen-rich supernovae, we see that there's essentially no difference. We cannot only do this for one epoch, we can do this for many epochs. The conclusion is always the same. Spectroscopically, it looks like a vanilla type 2 supernova with no signs of, let's say, a CSM interaction. And this is also the same picture that we see at late times. So in red, you can see a 5-hour spectrum a 4-hour spectrum that we obtained with the VLT at roughly should be 325 days after peak, so close to 450 days after first discovery. And in black you can see a comparison to 1987A. So most of the features have a correspondence. Depending on how you scale it, so meaning which kind of feature you want to match. So here you need to scale it by a factor of 1987A by a factor of 200. If you want to measure the forbidden oxygen 1, only a factor of 100 is needed. But if this is more important for you, then you need to only scale it by a factor of 50. So the punchline is spectroscopically it looks similar to 1987A, but it is much more luminous. And the scaling factor of 100 is roughly 5 magnitudes. And this is what we observe at early times, that this object is 4 to 5 magnitudes more luminous than 1987A. So, but we have no idea why this is actually, why they are so similar, but why is then the light curve so dissimilar? And this is another interesting avenue for theoreticians. I would like to skip this and go to the next object. So, so far I've shown you 2 examples for Pair-Instability Supernovae. We have also found a very interesting case, or very interesting supernova that we think is related to a pulsational Pair-Instability supernova explosion, but also fairly, let's say, exotic. It's not, yeah. So, and it was caught by the because of its rapid rise. So this infant supernova group within ZTF saw that there's an object rising very rapidly. We triggered immediately spectroscopy. So 24 hours after the first data point here, we had a spectrum from Keck. And you can see the spectrum here after we removed the blackbody continuum. If the blackbody continuum would be shown, then this would go clearly up because the object is hot. And when you see this kind of spectrum, or if you're familiar with infant supernovae, and you see such an emission line spectrum, you would say, okay, well, this should be produced by CSM that is very close to the progenitor star. And we somehow see here the response of this CSM to the incoming radiation field from the shock breakout from the supernova explosion. So the material here should then tell you something about the composition of the progenitor star shortly before the explosion. And you might say, okay, well, if you take an average star, then most of the material should be produced by, or should come from hydrogen, from helium, maybe some carbon, nitrogen. So the thing is, when you do the line identification, most of the features cannot be attributed to the most abundant elements in the universe. Instead, most of the features are produced by silicon 3 and 4, sulfur 3 and 4, and argon 3. Some weaker features can be attributed to helium 1. We have also another helium line, so we are sure about this. There's also some carbon. So silicon, sulfur, and argon is material that is formed during the oxygen burning phase, just months before a star explodes. So if you think about this, this is material that is usually buried under lots of material from lighter elements like carbon, nitrogen, helium, and hydrogen. So, but we don't see this material here. We see here a circumstellar material that is depleted in the lightest, most abundant elements in the universe, but it's highly enriched in the rarest elements a star forms throughout its life. So, to make this even more puzzling, these features show some of these features show clear PISNe profiles with velocities of around 1,500 kilometers. The fastest part of this PISNe profile moves at around 3,000 kilometers. So this is usually, these are velocities that are not comparable to supernova ejecta, but more material that a star lost due to an eruption, due to mass loss, to stellar winds. And we do not only see this kind of spectrum in our first epoch. These features persist for about a week. They become weaker with time, but they're always there. Between day 10 and 20, the character of the spectrum changes completely. The black body subsides, the narrow emission lines go away. But now we see this kind of spectrum. So we call this a pseudocontinuum, and this is essentially produced by iron that was in the, well, this is not freshly nucleosynthesized iron. This is iron that the progenitor star already had when it was formed. And iron has so many lines that if they move at some small velocity, then these lines become blended and they form a pseudocontinuum. And this is what we see here. And you would also expect to see a rise of this continuum from the red to the blue. This has been observed in many, or in other supernovae before that were engulfed in thick CSM shells. The difference here is that none of them has ever shown then emission lines from silicon sulfur. Instead, they have usually shown hydrogen or helium. So the question is now, how much silicon and sulfur do you need in that CSM? Not only in a relative sense, but also in absolute sense. For this, we got Luc Desart involved. He's a radiative transfer person who worked a lot on, on supernovae, and he has a grid of helium star models, and he went through his grid of models, and he to look for a model that has a significant, or a shell with significant silicon sulfur mass fraction, and the conclusion was he needed to take the most massive models in his grid, and there the oxygen core has a significant silicon sulfur mass fraction. This oxygen core is also fairly massive, around 3 solar masses, so it's not little. And this is, So he took this, he took this model, stripped it down artificially to the oxygen silicon shell, deposited a power of 10 to the 43 ergs at a velocity of 1,000 kilometers, and then his result was this red spectrum. And when you compare it to the black spectrum that we observed, you actually see an excellent match in terms of relative and absolute strength, and also the width of the features. So that tells us immediately we don't need a crazy high relative mass fraction in silicon and sulfur. A low abundance suffices, but we need a fairly massive CSM on the order of a few solar masses. And this is only for the spectrum at day 1. So as we sweep up, or as the more and more material gets swept up, this CSM mass will only increase. So we are likely dealing here with an extremely massive star, which means, again, because this is not, the composition is rather exotic, it cannot be a regular core collapse supernova, but it has to be some kind of exotic channel. So, and this brings pulsational Pair-Instability Supernovae to the table. And this is also why I'm here, why I want to talk with Ken Chen, what he thinks about this kind of object. So it turns out that in terms of the composition of this oxygen core in the helium-12 model, this is somewhat similar to the oxygen convective shell in a much more massive helium star. So this that helium star model has a mass of 60 to 61 solar masses. And so this is such a massive star can experience recurrent pair instabilities. And this mass is actually so massive that it's close to a full-blown pair-instability supernova. So why this is important is the following. So when you're so close to a full-blown pair-instability supernova, the star can also lose much more mass than it usually would. So Stan Woosley, who was involved in our project, said the following. So we have this kind of star. It undergoes its first pair-instability episode, and during this pair-instability episode, it loses, I think, 17 solar masses of material, and it strips the star down to the neon shell. At that point, the star is almost unbound, because we are also very close to the pair-instability limit. So after a few thousand years, the star experiences another episode, and then another, and another, and another episode. And with each new pair creation episode, it loses more material, and eventually it will also eject material that is rich in silicon, sulfur, and argon. So, and then the scenario that we would have is that we have here our star. It has these mass ejections, and then eventually the interaction between, or the collision between these between two shells that are rich in silicon, sulfur, and argon produces the transient that we observe. To make this a bit more concrete, the Keck Observatory created a nice animation for us, and this is shown in the video, so you can see the progenitor star. You will see now two things. The star will undergo, is already stripped, very much stripped at this point. It will experience a pair-instability episode, ejecting material that is rich in silicon, sulfur, and argon. You can see this here. The colors were chosen to reflect some of the typical colors that we associate with silicon, sulfur, and argon. So the star goes through a pair-instability episode, becomes a bit dimmer. After some time, it gets brighter again because the fusion is again more intense. And it experiences another pair-instability episode, which you can see here. At some point, these two shells will collide, and the collision between these two shells produces supernova 2021 YFJ. We have chosen a rather dramatic ending, not because we have data for that, but we wanted to show that this is not somehow a gentle process, but it can be very intense, liberate or converting a lot of kinetic energy into radiation. So, and this brings me to the last bit of the talk. So now you have seen our observations. You have seen the puzzling, or the interesting, but also puzzling results. And the question is, what does theory say about this? And also, where would we like to see maybe advances in the models? But of course, I'm not a theoretician, so the people who are familiar with that should chime in. So the important thing is, existing pair-instability supernova models can evolve very massive stars to the point of explosion. They can create these explosions. However, when the light curves are calculated, these explosions are taking the star out of its natural habitat, where the star lost all of its, or shedded a lot of its material. They take it out, put it in a radiative transfer code to calculate the light curves. And then they conclude, okay, the supernova or pair-instability supernovae have to be red, and so on, because there is so much nickel or a few tens of solar masses of iron group elements. The problem is these calculations, they have ignored the fact that there is a lot of material that the star could have lost, and the interaction of the supernova ejector with this material that they ignored could actually lead to a significant boost of the flux in the blue part of the spectrum. We can understand this approach. The problem is it was never validated that this is a good assumption. And so we would like to actually encourage theoreticians to investigate what is the impact of CSM around these stars on the observed light curves and spectra. For hydrogen-rich pair-instability supernovae, the situation is similar, but there's another complexity. Because the star has a hydrogen envelope, it can also lose an arbitrary amount of this hydrogen envelope. There could be stars that have retained most of its hydrogen envelope and stars that have retained very little. But there's an entire spectrum. The available models only considered two extreme cases, and it's not clear what is actually the entire spectrum. And last but not least, pulsational pair-instability supernova models are extremely challenging computationally, and it would be also nice if more work would be done in this regime to get a better understanding of not only how these stars could evolve, but also how light curves look like, how spectra look like. The spectra are current. At the moment, there's no prediction from a pulsational pair-instability supernova model on observed spectroscopic features. And the time is, or we would like to have these things actually as quickly as possible, because we are now at a stage where a new set of facilities are starting to observe a part of the transient phase space that was previously completely inaccessible. And this is the high-redshift universe, a regime where the stars were less chemically enriched than today's stars. They were also could have also been more massive than today's stars. And these are we could see here a zoo of supernova explosions we haven't even detected, for which we have no analog at low redshift. So, and there's some groups would also like to detect pair-instability supernovae in this treasure trove of supernova explosions in the high redshift universe. The problem is when you take Rubin, Roman, Euclid, or JWST, and these are very sensitive facilities, but these facilities would only give you light curves like this, a few data points in this filter, a few data points in that filter. So very sparsely sampled light curves compared to what we are used to. And then you need to make some hard cuts on how to identify transients of interest. So some groups have suggested that you could use color selection criteria to identify transients of interest. So in this paper by Moria et al., they took templates of type 1a, type 2, supernovae, superluminous supernovae, pair-instability supernovae, computed the color at various redshifts, and plotted it against a magnitude, and they concluded, okay, if you have a type 1a, well, they should populate this part of the parameter space. If you have a type 2 supernova, well, then they're here. And if you would have pair-instability, you're covering this part of the parameter space. So when you do that, then you would conclude, okay, well, there is a part of the parameter space that is only populated by pair-instability supernovae. So you could use this to identify transients of interest. This is a valid approach. The problem is there are several key assumptions. First of all, it assumes that your models are right. It assumes that you know how the population of supernova explosions in the high redshift universe look like. And also that there is no unknown class of supernovae that hasn't been detected yet. So there are lots of assumptions here, It doesn't mean we shouldn't do it, but these are strong assumptions. So while people are pursuing this, we need to continue finding transients that have light curves similar to Pair-Instability Supernova models. We need to obtain for those objects exquisite data sets in terms of photometry, spectroscopy, covering hundreds of days. But we also need new types of observations to directly test assumptions of these explosion models. So, and most of the progress could be done with JWST, and the reason is the following. So you see in this plot a spectrum of a type 1a supernova in black, and because type 1a supernovae produce a lot of nickel, you would expect to see a lot of nickel features in the optical, near-infrared, and also at longer wavelengths. If you take a core collapse supernova, then this regime between 0.6 and maybe 1.4 micron will be dominated by low mass element, by intermediate mass elements. You will hardly see the ion group elements. This regime here, between 2.6 and 3.5 micron, is actually quite interesting because this is in this regime you will only see the ion group element lines. So if you would have a near spec spectrum targeting this regime, you could directly look for the ion group element lines, and based on those ion group element lines, you could directly compute what was the nickel yield. So you could do this for some redshift range, but you cannot push this to very high redshift because you need very late time spectra, and if you have a supernova at redshift 2, redshift 3, the time when this is happening in the observer frame is happening at 1 plus redshift. So instead of maybe doing an observation at 1 year, a redshift 2 supernova would require that you do this observation at 3 years after the explosion. So very different timescales. Then something that has not been properly investigated yet, and there are also a lot of that would be nice to see updates. So this paper by Schneider et al. Suggests that the conditions in pair-instability supernovae can be very supportive for fast and efficient dust formation. You can see here 3 different channels of hydrogen poor pair-instability supernovae, and on the x-axis you have the time since explosion, and depending on the mass range between 150 to 250 days, you would expect to see the onset of dust formation, and not just by a little bit, but by a lot. So this is 10 solar masses here. So and this would make these kinds of explosions faster, more efficient dust factories compared to ordinary core collapse supernovae. And to put this a bit in context, if you have an ordinary core collapse supernova, they only produce between 0.1 to 1 solar mass after many years. Pair-instability supernovae are, according to this model, expected to produce even 10 or more solar masses of dust. Quite interesting. But this is theoretically a very underexplored regime, and there's also a question: you can produce a lot of dust, but you also destroy a lot of dust. What is here the balance? And to show you that this is not just some hypothetical scenario, so we did the exercise, and we said, okay, let's assume a pair-instability supernova at redshift 0.17 produces 1 solar mass of silicate dust. This is the dust composition that you would expect for this kind of explosion, and dust temperature of roughly 150 Kelvin, also in a regime that is predicted by these by this model. And then you would expect to see this kind of SED. So the brightness would vary something between 19 magnitudes, 23, 24th magnitude. And on the lower panel, you can see the broadband filters of the MIRI imager. So if we put this into the JWST exposure time calculator and ask the question, okay, how much observing time would we need if we observe in all of those filters with this kind of SED, then within a fairly reasonable amount of observing time, you could get high signal to noise detections in all of those filters, meaning that you could maybe also catch pair-instability supernovae by their dust production. But this assumes that we understand dust production in those extreme stellar explosions. And this is also a regime where more theoretical work needs to be done. Last but not least, we could also play the opposite game and say, okay, these objects are not pair-instability. What is the alternative? And one of the alternatives is that maybe they are magnetar-powered. And this is usually, usually this is a very popular scenario these days for supernovae. Everything is magnetar-powered. I'm not commenting on that further, but this is somewhat a working assumption. If you have a magnetar-powered supernova and you observe these kinds of objects maybe years later, you would several models conclude that most of the emission at late times comes out through this neon 2 12.8 micron feature. It is the most luminous feature throughout the entire late time evolution of a supernova. All of the other diagnostics that are accessible in the optical, they are much fainter, and they also show a very strong time evolution. So this neon 12.8 micron feature could be detected also with JWST. So this is, in this plot, you can see the sensitivity of the MIRI mid-resolution spectrograph. And here we would have our 12.8 micron feature, and the MIRI sensitivity would stays fairly constant out to 18 micron, and this would translate, or based on that, we could suggest that that this 12.8 micron feature could be detected out to redshift 0.4. So this is another angle of how to pin down the progenitor channel of these extreme explosions. So with that, I'm very sorry that I'm over time. I would like to conclude. So over the past years, we have found some very extreme stellar explosions, and those objects have properties that match very much match predictions of pair-instability and pulsational pair-instability supernova models. We still call them candidates because there are a few open questions, not because we have inadequate data, but because the properties that we observe are in a regime that we cannot test with the existing models in hand. And we need improved models because we need to understand, are these genuine pair-instability or pulsational pair-instability supernova explosions, or are they not? The implications are far-reaching in either scenario, because if we know that these are pair-instability supernovae, then or pulsational pair-instability supernovae, then we know how to look for them at high redshift. If we know that these are not, they do not belong to this exotic class of transients, then it also means that we do not understand that our knowledge of stellar evolution is not complete yet. And like versa, it would tell us that there is a class of supernovae out there that can mimic properties of pair-instability supernovae. And this would also affect us how to detect these objects at highest redshift. And the reason why this is important is because we are on the cusp where a lot of new facilities are trying to catch transients in the high redshift universe, and in particular trying to catch the pair-instability and pulsational pair-instability supernovae. We propose that progress could not only come from the theoretical side, also from the observational side. We need to continue with the follow-up, extensive follow-up of those candidates, but we need to get Webb, which is very hard to get, but we need to push. And last but not least, we are now in the era where we can combine different transient surveys to get exquisite light curves covering many hundred days. And that's something that hardly existed for any of the candidates. And with that, I would like to finish. Thank you.
Thank you very much. Really nice talk. And any questions? We'll see.
Would you have any comments on the difference in CSM properties between the Pair-Instability and normal core collapse supernova?
We have, so in the case of 18 IBB, the CSM is depleted in hydrogen and helium, but it's rich in oxygen. So it's highly processed gas from the or material from the progenitor star. We have also detected some regular core collapse supernova with similar features. At the moment, nobody has tried to properly simulate that in the sense of which kind of compositions would you need, which kind of masses would you need. Considering that pair-instability supernovae are, in general, or the ones that we detected, are very luminous, you would need a lot of CSM material. And this would be a distinguishing features compared to ordinary core collapse supernovae, which are much less luminous, and where you would need then also much less CSM to produce the features that we observe in those in the ordinary core collapse supernovae. So in terms of composition, maybe not a difference. The CSM masses could be starkly different between the supernova classes.
Thank you.
Mm-hmm.
Any other questions or comments?
What is the rate for like PISN? Does that match with the gravitational wave observations?
So, okay, so right now we own, so 18 IBB is by far the most compelling candidate for pair-instability. If we take this object, the rate would be consistent with what LIGO people would also measure, but with one object, the error bars are enormous. So it's hard to say at the moment. We need more objects. They're also simplifying assumptions that what is the luminosity functions of pair-instability supernovae? How does this is currently not included in the rates, but also for the LIGO people, how secure are they about their rate estimates? What are the assumptions there? Yeah, more work needs to be done.
So how would the velocity evolution of the exacta look like for these PISNe?
Yeah, so this is a very good question. So for our, okay, let me go back. Okay, so for this object, we have our spectroscopic sequence starts here. So up to here, we still see nice photospheric phase spectra. Here things get more complicated. So over this time interval, which is approximately 100 days, we don't see any measurable velocity evolution. When you look at pair-instability supernova models, they predict some velocity evolution. But the question there is also, how much can you maybe tune that? Because these models that currently are available, they were not tuned to our observations. Yeah.
Could you say more about the host galaxy?
Yes, always metal poor. So in this guy it was less than half solar, but also for the other two it's less than half solar, but it's not less than 10% solar. So it's low, but not extremely low metallicity.
So is the local environment
Unfortunately not. So all of those objects are at redshift between redshift 0.1 and let's say 17. So even with AO, there's no way of resolving the environments properly. It's the host galaxies there are on the low mass side because they have a low metallicity, but yeah.
Is it on the main sequence or
yeah. It is mostly consistent with the main sequence. Yeah.
Any other other final comments? Questions? Okay, so Steve will be here until Friday, so you're welcome to check in at his guest room, the visitor office.
Yeah.
And that's thanks Steve again.
Thank you.